Alrighty, so today's video is on real gases and equations of state, right? So we've previously talked about this idea of ideal assumptions, right? And you probably are familiar with it in high school, right? The ideal gas law is something that most students have done in their intro to chemistry course. But of course, we know that ideal gases don't always apply. And so knowing how to account for non-ideality is what we're going to talk about in today's video. And we do that through equations of state. So let's get right into it. We have our whiteboard, and I'll just write out our ideal gas law here. PV equals nRT. Now, there's a couple of key assumptions that the ideal gas law makes, right? So the first thing is that the gas molecules are have negligible volume. So each gas molecule is what we know as a point mass. In other words, it takes up no space, right? And then the other assumption is that the intramolecular forces, so these are stuff like the dipole-dipole, hydrogen bonding, um, stuff like the small dipoles that you get. I forget what the name is called, where you get like the small instantaneous dipole, like the dispersion forces. Um, but the key here is that these things, these intramolecular forces, we assume are zero or not equal, not is equal to zero. So there is no intramolecular forces. And so the question is, at what conditions are these actually realistic, right? So let's talk about the negligible volume. If we have a lot of space, then it's fine. Essentially, if there's negligible volume, it's unlikely that a gas molecule will collide with another gas molecule and they'll get in each other's way, right? It's only when you increase the pressure to a certain point where you've like cramped up all these molecules. And so you can imagine we've like cramped up all the molecules in this really, really tight space, so high pressure. And so now these molecules are actually getting in the way of each other. And so that is a part where we have a non-ideality, right? So this negligible volume is we want low pressure. So at low pressure, negligible volume, that is a valid assumption, right? And now if we look at intramolecular forces, it's the exact opposite, right? So instead of pressure, you have to think about, okay, what could cause these intramolecular forces to actually be negligible, to be equal to zero? And so in this one, we can look at the temperature. Temperature really is just the measure of the average kinetic energy of these molecules. So you can imagine if these molecules are moving really, really fast, they're not really having enough time to basically exert enough force on each other, right? Or the force that is exerted is negligible compared to if they're moving really, really slow. So if you have slow moving molecules, then those forces are going to actually have a bigger play on this on the overall gas. So you can see the intramolecular force is actually equal. This assumption intramolecular force is equal to zero is when we have a. So this is why we say that this ideal gas law typically applies at low pressure and high temperature, right? Now, of course, in chemical engineering, you'll have processes or gases that are not at low pressure, at very high pressure, or you'll have gases that are at a low temperature. So in this case, we see that, okay, maybe we have some non-ideality coming in play here, right? And so I think one way to think about this is if we take our ideal gas law and we divide by nRT on both sides, in the ideal case, we get 1, right? Now, let's suppose we don't have an ideal gas and we just make this some unknown. So we'll call this Z. This is known as the compressibility factor. So this is kind of a good way to imagine exactly like, okay, what how non-ideal are we, right? Obviously, if it's close to one, it's pretty much assumed that the compressibility is, or it's pretty much assumed to be an ideal gas, right? If compressibility equals one, we're pretty much ideal. And the further away from one we are, the less compressible, or the less ideal we are, the more non-ideal we are looking at. And actually, there are a couple of compressibility charts that we can actually look at and use to actually see, okay, how far from non-ideal conditions are we actually getting for? And these use what's known as the critical pressure and temperature. That's how you read those charts. Perhaps I'll make a video on that. I don't really want to go into that in this video. But the most useful thing that I want to talk to you about is actually a quantitative way, like an equation, right? Because we're engineers, we like to use equations. So I want to give you an equation that you can actually use for solving in the non-ideal case. So let's move down here. So suppose now we're dealing, okay. So the first equation of state that I want to talk to you about, and which is probably the most common and most commonly heard of, is known as the van der Waals equation of state. And it basically looks like this. P plus A over specific volume squared times the volume minus B is equal to RT. So we're using specific volume, so there's no n term here, right? And so basically this is pretty similar to the ideal gas law, except we have these two extra terms, the A term and the B term, right? And so basically each one of these is a correction for one of the assumptions we made earlier. So this B term is the molecular volume correction, right? So remember, the first assumption we make is that each molecule is negligible volume. It takes up negligible space. We can consider them point masses, right? But as we know, real gases do actually take up spaces. So we actually subtract this from the volume so that we account for the actual volume that is available for the gas to move in, right? So if the total volume is, I don't know, say you have 100 liters, and then the gas molecules take up 1 liter, then the real volume that the gases have to move in is 99 liters, right? Something like that. And then, of course, you can imagine that this A over B hat squared term accounts for the intermolecular forces. So this these attractions, right, between the two molecules essentially reduce the effective pressure that the molecules exert on the container walls, right? So if you can imagine, I have a container, and I have this molecule in the center, and then I have all these other molecules. Because there's intramolecular forces, they're kind of pulling each other closer. And by pulling each other closer like this, they're not exerting as much pressure on the walls. So we add this AV squared back to the measured pressure to get essentially the effective pressure, right? So even though we might have a container and we measure the pressure to be 1 atmosphere, for example, we have to understand that there's some pressure that's not being exerted because the molecules are attracting each other away from the walls. So there's actually extra pressure in reality. So we add that back. Now, of course, if you get A equals 0, B equals 0, then this just simplifies to PV hat equals RT, which is basically just the ideal gas law, right? So essentially van der Waals is very simple. It's ideal gas law plus two physical corrections essentially that will allow you to um, change the value. Now, you might be asking, how do you get A and B, right? Well, A and B are tabulated, right? So you don't get them from scratch. I mean, you can, not impossible. I won't show you how to do that, but you can get A and B from tabulated values, like from Perry's or Wolfram Alpha, etc. Whatever your preferred method is, right? So if you actually have the A and B for the species, you can actually do the correction as you need, right? So for example, and we'll do an example as well with CO2. For CO2, we have A equals 0.3658 pascals meters to the sixth over mole squared. And then we have B is equal to 4.286 times 10 to the minus fifth meter cubed per mole. So we can actually use these values to solve in non-ideal cases. So let's actually go through a practice problem here. So I want you to suppose we have 1 mole CO2 at temperature equals 320 Kelvin, pressure is equal to 10 megapascals. Now I want you to find the molar volume using the ideal gas law, and then I want you to find the volume using the van der Waals equations. And then we can compare to see how far or close we actually are. Right? So basically, ideal gas law, PV equals nRT. Let's write down all this information that we have. So obviously N is equal to 1 mole. Temperature equals 320 Kelvin. Pressure is equal to 10 megapascals. So that's 10 times 10 to the sixth pascals. And then, of course, we know R is equal to 8.314 joules per mole Kelvin. Everything's in SI units, so this should be pretty straightforward. Basically, we plug in our values. We get V equals nRT over P. And if you did all these calculations, you should get 2.66 times 10 to the minus fourth meter cubed per mole. Or a nicer number would be 0.266 liters per mole. Sorry, I automatically put this into specific volume. This is meters cubed in liters, right? Obviously, because we're in one mole, this is per mole, but let's use the units that were here. We're solving for volume here, so we have 0.266 liters. So that is our final volume for 1 mole of CO2. Okay, now we do the same thing, but with van der Waals, right? So remember that van der Waals is P plus A over V hat squared times V hat minus B is equal to RT. Basically, what we first want to do is actually expand it into the cubic equation. So we'll multiply everything by, we'll expand it and multiply by V cubed. So this actually becomes PV hat to the cube minus PB minus, or sorry, PB plus RT, V hat squared plus AV hat minus AB equals 0. And then it's just a matter of plugging in the numbers. Uh, Same numbers as before, and just remember that A is equal to 0.3658 Pascal meter cube per mole squared, and then B is equal to 4.286 times 10 to the minus 5 meter cubed per mole. So if you plug in these values plus the values we had earlier, the cubic becomes 10 to the 7th B hat cubed minus 30,089 B hat squared plus 0.3658 B hat minus 1.568 times 10 to the minus 5. This is equal to 0. So now we can actually solve this cubic equation, right? Now, I won't go into details on how you can solve this. You have many options, Wolfram alpha. You can solve it numerically. Whatever method you want to choose, I'll just give you the answer here. We get v hat is equal to 9.98 times 10 to the minus fifth meter cubed per mole. Since there's only one mole, we know that the volume is equal to 9.98 times 10 to the minus fifth meter cubed, which is equal to 0.0998 liters. So now let's just compare those two values. The ideal gas law gave us 0.266 liters, whereas the van der Waals equation gives us 0.0998, right? So pretty significant deviation, um, as you can see here. And if you look at the actual temperatures, it's fairly high pressure. 10 megapascals is no joke. And then the temperature is not that high. It's a 320, which is around 50 Celsius, right? So, it's hotter than might be comfortable for us going outside. But it's not super, super hot or anything like that. Um, so clearly there's definitely a difference between what the ideal gas is stating, right? What we're actually seeing versus what value we're actually getting from the ideal gas law. So actually, one thing that might be interesting here is to actually compute what is the compressibility. So actually, let's do that right here. So let's compute the compressibility. So remember, the compressibility is equal to PV over nRT. So we have 10 times 10 to the sixth times the volume, which is 0.0, sorry, got to keep everything SI units, 9.98 times 10 to the minus fifth meter cubed over N is 1 mole times 8.314, and this is joules per mole Kelvin, times, lastly, the temperature, 320 Kelvin. And so if I were to actually solve for the compressibility here, I would get a compressibility of 0.375, roughly speaking. So clearly a very significant deviation from the actual ideal gas law, right? So in this case, it's very clear that we need to be using something that is a non-ideal to actually do this estimation of the volume. So to end this section, what I do want to do is share some other equations of state that you may come across in your studies. Now, if you're a person who's using Aspen a lot, like Aspen simulations, you'll probably see in the beginning when you're in the properties tab, you need to actually specify what equation of state you're going to actually use to estimate the physical properties of your simulation, right? So there's a couple of ones that are out there that you can use. So one is Peng-Robinson equation of state. Now, this is commonly used in the oil and gas industry. It's pretty popular there. It's very complicated. I won't, I can show you the equation. You can look it up online, but it's more complicated than the van der Waals, but essentially it's the same thing. You have a pressure correction for molecular volume and one for intramolecular forces, right? Another thing is Redlich-Kwong. And these are all just different ways of essentially estimating the essentially the physical properties of the gases that you're working with, right? And Aspen does have a nice guide that allows you to look through and see, okay, based on what are the components that you're working with, which equation of state do they recommend? So like for if you're working with oil and gas, hydrocarbons, right? If you're working in that area, it'd probably be good to use the Peng-Robinson equation of state. That'll probably give you a good, accurate estimate of what the gases are going to behave at versus something like a Redlich Kwong or ideal. Like the amount of times you'll use the ideal situation is very, very little and far in between. So, anyways, this is a short introduction to non-ideality. I hope you found this helpful and good luck with your studying.